Right, the next example is sourced from the world of packaging. So we have a cardboard square sheet of side 24 centimeters, and this is to be used to construct an open box by cutting out smaller squares of equal size from the corners and folding up the edges. Find the dimensions of the box possible with the largest volume. So from what we talked about before, clearly for this example, the objective function is going to be the volume, because we want a box with the largest volume. The constraint is going to be the amount of cardboard we have. We only have a square of side 24 centimeters, so that is what makes up our constraint. So this is what happens in this type of thing. So we cut out equal squares from the corners, and then we fold the resulting edges. So I'm just going to put a dotted line here. So if we imagine that the squares are of equal size, let's call the size X. Okay, so we are going to cut out these. So when we cut out these, we are going to end up with something that looks like this. Okay, now if we fold the flaps along the dotted lines, then we're going to end up with a box like this, an open box. Of course, this is going to be a box of height h, because the height is going to be equal to the side of the squares, smaller squares that we cut out from the corners. So from this to this, and then we fold, and then we have our box. Now the size of the square is the thing that's variable here. So we could cut out a very small square at the edges. If the square we're cutting out is very small, then we end up with a very wide but shallow box. Okay, so that's one extreme. Got a very wide and shallow box. Or the other extreme, of course, this box is shallow, so it's going to have a small volume, but then we can keep increasing the size of square we cut. As we keep increasing the size of square we cut out, the volume is going to start increasing of the box. The other extreme is if we cut out a very big square out of the edges. Then in this case we are going to have a very tall box. So these are the extreme from this one to this one. At some point as we vary x, at some point we should have a value of x for which the volume of the resulting box is maximum. So if we go back to this one here, the height of the box we've already said is going to be x. The base is going to be a square, so, and it's going to be a square of size 24 minus 2x, because we cut out x from each end of the box. So it's going to be 24 minus 2x here, 24 minus 2x. So that means the volume of the box is going to be x, which is the height, 24 minus 2x, which is the length, 24 minus 2x, which is the width. So this, if we factor out 2 here and 2 here, you can write this as 4x into 12 minus x squared. Then if we expand this, this is 144 minus 24x plus x squared. If we multiply x into this, it will be 4 into x cubed minus 24x squared plus 144x. I've just written these in the reverse order. So that is the volume for which we want to find maximum. So we need to find x for which this function is maximum. So of course, to do that we need to find the derivative. Derivative of this is going to be 4 into 3x squared minus 48x plus 144. To find the stationary points, we'll equate this to 0, but for now I'm going to work out the second order derivative. It's going to be 6x minus 48 here. So now let's find the stationary points. So we need to take this and equate it to 0. So 4 into 3x squared minus 48x plus 144 equal to 0. We can divide by 4 and we can divide by 3 as well, because all these numbers are factors of 3. If we do that, this thing is going to give us x squared minus 16x plus 48 equals to 0. So as a quadratic, we can solve it any method we prefer. If we factorize this, factors out to x minus 12 into x minus 4. So that means the stationary points are either x is 12 or x is equals to 4. We want the one that gives us maximum volume. So we're going to use the second order derivative to test whether each of these is giving us a maximum or a minimum. So if you start with x equals to 12, we are going to plug this into the second order derivative here, which is 4 into 6x minus 48. So it's going to be 6 times 12 minus 48. If you work this out, it gives us 48. Now if the second order derivative is giving us 48, this is telling us concave up, because it's greater than 0. So that means at x equals to 12, the graph is going to be something like this, and this implies relative minimum. So that's not what we're looking for. In fact, if you plug in x equals to 12 into the volume function here, you're going to see that this gives us a volume of 0. And if you take it, and this is very important for these applied problems, whenever I find something from the mathematics, always related with the practical situation of the problem. So for x equals to 12, this thing is saying we're going to cut out a square of size 12. Use a better color here. I'm going to cut out a square of size 12. Let's use which one are we going to use? Let's use green. I'm going to cut out a square of size 12 here. Cut out a square of size 12 here. Cut out a square of size 12 there. Cut out a square of size 12. If I cut out a square of size 12 from each corner, we won't have anything to work with, because so we cut this thing out, we throw it away. Cut this out, we throw it away. That's basically the whole square that we started with, cut out, and we lost. So we are going to have volume 0 because of that reason. So these squares can be as big as possible, but if that square is of side 12, then we are going to have volume 0. Now let's check the other value, or the other stationary point, which is x equals to 4. Okay, so if again we plug in to the second order derivative, is going to be 4 into 6 times 4 minus 48 this time. So this is 24 minus 48, going to be minus 24 times 4. Just one moment. Right, just a minor issue here. Actually, this should be 96. So 96 there. Of course, the conclusion is still exactly the same because it's positive. And back to this one, it's going to be negative 96, which is less than 0. So it implies that the graph is concave down at x equals to 4, and so we have got a relative maximum. So that means x equals to 4 is the one that gives us maximum volume, starting with the square sheet of size 24. So that means the dimensions of the box will be, remember, the height is x, which is 4, then the base is going to be a square of side 24 minus 2x, so that's 24 minus 8, so it's going to be 16 centimeters here and 16 centimeters there. So that is going to be the dimensions of the box with the maximum volume that we can get with that rectangular cardboard of square cardboard of size side 24. Okay, the next example is also from the world of packaging, but it involves a cylinder. We will do it in the next video.